So let me start from the fact that we have two systems, 1 and 2. And all we know is that the total angular momentum, or J1 squared of 1, is given by J1 plus 1 h bar squared. And the total, the angular momentum of J2 squared is given by J2 plus 1 h bar squared. So I'm going to, in general, use units where h bar is set to 1. Okay, so it's not very hard to put it back in. And what we don't know is that we don't know the orientation of these two spins. Okay, so there can be any orientation. So so first we assume, so if the first system is in state psi 1 and the second system is in psi 2, then the combined system is in a tensor product state of psi 1 tensor with psi 2. Okay, so this is basically what we expect. Well, this is basically one of the assumptions of quantum mechanics. Okay, so now what we want to find out, so let's call this state psi. What we want to find out is that we want to find out the possible eigenstates of the combined system in the, we want to find the possible eigenstate of the combined system as, eigenstates of the total angular momentum operator, which is, J squared. What is J squared? J squared is J1 plus J2 whole squared. Okay? And we want to find it as an eigenstate of also a z component of the total angular momentum operator, which is going to be J1z plus J2z. Okay?
Sir, is it J1 plus J2 whole square or J1 square plus J2 square?
No, it's J1. So the total angular momentum of the system is J, and that's going to be J1.
Oh, right. Yeah,
right?
I see. Yeah.
So we know that we need to, and it's easy to verify because, J1 commute with J2. All components of J1 will commute with J2. Using that and using the fact that, J1 and J2 themselves are angular momentum operator, you can show that J itself is an angular momentum operator, okay? It's an angular momentum operator, meaning that it satisfies the same, algebra as J1 and J2. Let me remind you what that algebra is. If I take Ji and evaluate the commutator with Jj, I get I epsilon ijk j of k. Okay, so this is the angular momentum algebra. And because J itself satisfies the angular momentum algebra, we can always construct J squared operator, which is going to commute with all the components of J. And therefore, the combined system will have eigenstates whose eigenvalues will be given by the eigenvalue of J squared operator and the eigenvalue of the Z component of Jz. Okay, just as before. Now, what we want is that we want to find psi as these states. Okay, we want to find what kind of, what are the possibilities psi can take, so that psi is a, we want psi is an eigenstate of, well, it's a simultaneous eigenstate of J squared and Jz. Okay, and we want to express, psi as linear combinations of tensor products of the form J1 M1 J2 M2. Okay, so this is what we want to do. So any questions about what we want to do?
No question, sir.
Okay. All right, so this is the mathematical problem that we have set ourselves. So before we go there, let me just remind you what the relevant operators are. So of course, J squared is one of the relevant operators that we need to understand. J1 squared, J2 squared, and then if I look at J squared, it's going to have the form J1 squared plus J2 squared plus 2 J1 dotted with J2. Okay. Now, we also have the raising and lowering operator. So if I have J plus minus, that would be given by J1 plus minus plus J2 plus minus, okay? Because J is given by J1 plus J2, and therefore if I construct J plus minus, this follows very easily. So from experience, we know that the things that are useful for us are the square of the total angular momentum operator. Sorry, let me be a bit clear. I get a bit confused, and I sometimes use total angular momentum to call this. This should really be the J squared operator. I should really not call it total angular momentum operator. This should be the total angular momentum operator. Okay. So, from experience, we know that the J1 square operator, J2 squared operator, those guys will be useful because, they have very nice, because we are expressing, we are using states which are eigenstates of these operators. And we also know that we are going to be, other useful operators will be JZ, as well as J1Z and J2Z. However, the other components of J1 and J2 are not very useful because, more useful would be to express them in terms of raising and lowering operator. So for that end, what we want to do is that we want to take this J squared expression and convert it into operators that we find useful. Okay, so let's do that. So this is something that I left as an exercise, and I want you to do this because you will get some experience dealing with tensor products of operators. So then it turns out that J squared is going to be J1 squared plus J2 squared plus J1 plus J2 minus, and then plus J1 minus J2 plus 2 J1Z J2Z. Okay, so this is something you have to show for yourself. Okay. As you can see, this is not going to be something very challenging.